Well, good morning, everybody, or afternoon, or evening. Well, welcome. Springs. Let's play. So, we need to talk about a couple things about springs. First up, though, is think about where do you see springs in your life. So, here's my list. I see springs in a lot of things. If you look close, you'll see springs in basically every piece of machinery, computing, whatever you have. Your Apple mouse that has one button, that's got a spring in it. Seriously, one button. Alright, let's jump in. Couple different things though. If you think of a spring though, as you compress a spring, do you notice that the force changes? At first it's easy, and then as you compress it, it gets harder and harder and harder. If you think about like one of those hand grippy things, that it's harder and harder and harder to push, but at first it's easy. Okay, so that's a big idea, is that springs do not have one force. Up to this point we've dealt with only stuff that has one force, but now we're dealing with stuff that has a whole slew of forces. It changes depending on how much you compress it. So let's play. We're going to compress a spring and store some energy, and so the equation that we have is called Hooke's law. I'll show you a picture in a second where it came from, but this is the guts of it. That as I have K, it's a spring constant, and it tells me how strong my spring is. X is how far I physically compress the thing. And so X is telling me that compression. The compression has to be in meters. Spring constant will show you the units in a second. But this is called Hooke's law. Negative. Don't get hung up on it. Trust me. So let's do a problem, and I'll show you Hooke's. So here we go. So a spring is pulled with 20 newtons of force and is stretched 5 centimeters. What is the spring constant? So we're going to call it number 1. So number 1, F equals Kx. So the force that was applied was 20. The X was 0.05. And if you look at my units, this is newtons and this is meters. So that's 0.05 meters. My spring constant is 400 newtons every meter. So that means if I had a spring and I stretched it a meter, I pushed it a meter, it would exert a force of 400 newtons. So the second one on this question is, now how much force will apply if it's only stretched 9 centimeters? So I don't know the force, but the spring is the same. So I have the exact same spring. I now plug in my distance, and I get 36 newtons right there. That's it. I know. Hooke's law. So what he did was he had to say, I got a spring, it's this long, I put one thing on it and it stretches a certain distance. If I stick something twice as big on it, it stretches twice the distance. Thus Hooke's law. We'll do some things in class with it. Potential energy. Now we get into the crux of what we need to talk about. So one is springs apply forces. The second thing is that springs store energy. They're a great way to store energy. So what we're going to do is we're going to think of how you load a spring. So to load a spring, here's your spring, and you compress the thing, you do work. Okay, and as you do work, where does the energy go? The energy goes into the spring as stored energy. So we're going to start everything with that. Second thing, if you look at your graphs, wait, sorry, I don't know which way to point. If you look at your graph, you don't just have one force. You've got a force that changes. And so it starts at no force with no stretch, and then it gets more and more and more. So you see that line going. And so what I can do is I can say, well, if this is a forced displacement graph, what does the area represent? You got it, my friend. Work. So now let's find out what that area is. So algebraically, let's find that area. 1/2 base times height. Are we good so far? I think we're good. So now we've got to do 1/2 base times height. So the base is x and the height is force. And so, but we know that force equals kx. So let's get force out of there. Let's get rid of it. So that we don't have to find the force every time we do a problem. So let's plug in kx for that force. We get 1/2 kx squared. That's the work that you did. So how much energy does the spring have? 1/2 kx squared. The U that you see here is not because we're the Union Titans, but instead it means potential energy. The letter U means potential. We're going to do 2 problems just to make sure that we're comfortable with these. Spring has a spring constant of 200. You can press at 12 and then launch a ball with it. What speed does the ball have? Well, let's think about my scenario. I start with a spring being compressed, and then the spring is not compressed and the ball is moving. So I think of my energy. What type of energy do I start with? I start with spring energy, and I end with motion energy. Now, assuming this is a perfect situation, I would say that the spring energy equals the kinetic energy. We know that that's not completely true. We know that there will be energy loss somewhere. So some heat or some friction is going to take it out. We get that. But let's assume it's a perfect situation. So 1/2 kx squared equals 1/2 mv squared. So 1/2 k, your x is 0.12, equals 1/2 mass times the velocity squared. Do a little math magic, and you get 7.6. And yes, those are all the decimal places you get. 2 sig digs, because this 200, if I had a period, there's 3, there's 2, ooh, there's 1. So technically my answer should be 8 meters per second, because I only have one significant figure here with the 5. So here we go. Now I drop a ball. What? And it compresses a spring. This is amazing. So I drop it from 5 meters up. It compresses a spring. How much does it compress? Well, let's think about the energy I have. I got potential due to gravity up here, and I have potential due to a spring down here. Maybe we can make them equal. So I can say mgh equals 1/2 kx squared. Mass, 1. Gravity, 10. Height, 5. Equals 1/2 k x squared. Solve for x. Solve for x, you get 0.57 meters. So really 60 centimeters. That's a big stretch. It's pretty cool. So tomorrow in class we're going to crank out and work with a whole bunch of spring problems. So I'll see you there. Have a good one.